It's bonfire night in the UK, and fireworks are going off randomly and yet consistently at an average rate of around 12 per minute. That doesn't mean there'll definitely be 12 in the next minute, but it does mean that on average, if you were to keep track of how many fireworks have gone off and divide by the amount of time that's gone by, you would be getting pretty much consistently a rate of 12 per minute. Now, you can easily scale this up. You could ask the question, how many would you expect to hear in the next 5 minutes? And it's just going to be 5 lots of 12, so maybe 60 fireworks in 5 minutes. Or you could scale it back and say, if you get 12 fireworks in 60 seconds, maybe you're expecting to hear on average 2 fireworks in every 10 seconds. But of course, that's just an average. And the problem becomes a bit more interesting to explore when we start asking, how likely is it that you really will hear 2 fireworks in the next 10 seconds? Or what's the chance of you hearing 3 or 4 fireworks in the next 10 seconds? Or perhaps waiting for an entire minute and not hearing any? What are these probabilities? And can we use the statistical distributions that we've already learned about to explore them? What about a discrete random variable? It makes sense that it will be a random variable because the fireworks are going off at random moments, and although the rate at which they happen on average is fixed and constant, it doesn't mean that the actual rate is reliably fixed and constant. The average rate is constant, but the actual frequency with which they happen, that varies. It's a discrete variable because there'll be a fixed, sensible number of fireworks. We just don't necessarily know what that number is. So you'll definitely have either 0 fireworks or 1 firework or 2 fireworks, etc. You can't have 3.7 fireworks. It's not a continuous variable like normal distribution would work with. It's a discrete variable, the sort of thing binomial might deal with. However, binomial can't work for this one. Have a think about what the conditions are for a binomial distribution and see if you can figure out what makes this situation fundamentally unsuitable for a binomial distribution. Okay, well, one of the main things here is that binomial distribution is designed to work with a fixed number of trials. How many trials are there in 10 minutes or 5 minutes or 10 seconds? How many opportunities are there for a firework to go off? Well, how many moments are there? Kind of depends how long a moment is. Can we treat a single interval of time as a trial? Well, let's see what happens if we try that. Let's see what happens if we assume we could use a binomial distribution. Seems like a reasonable approach to say let's break down our minute into 60 1-second intervals, and each interval could be a trial. So in any given trial, you've got a 20% chance of having a firework go off. So x is modeled by a binomial distribution with these parameters, and it checks out so far. We can work out the expected value by saying 20% of those 60 seconds are likely to produce a firework, so 12 fireworks. However, this assumes that you can never get more than 1 firework during the same 1-second interval. It would be us effectively reducing this to tossing a biased coin 60 times, and at each coin toss you either get tails or you don't. Well, that's not quite how the firework situation works. There's nothing stopping you getting more than 1 firework within any given second. And in fact, realistically, if there's a 20% chance of a firework going off in any given second, on average, then you give it enough seconds, you wait a minute, you wait 10 minutes, you wait an hour, chances are you're going to have a few seconds where you do get multiple fireworks going off, even within the same second. So what happens if we just break it into smaller chunks? Maybe we only look once every 10th of a second. We look every 100 milliseconds, and we're now thinking of 600 different possible intervals that we're considering. Every single trial of our binomial is now only a 10th of a second long. And we're still getting the same expected value because even though I've increased the number of trials, I've proportionately decreased the probability. There's only a 2% chance within any given 10th of a second. But why stop there? Why not go a bit further? We could even move all the way up to milliseconds. And this, in fact, is the kind of thing you do if you're programming this. If you wanted a computer to emulate this kind of behavior, then you could do a lot worse than just say, yeah, it's running at 50 frames a second or whatever. So every single frame that goes by, let's give it a certain probability of this thing happening. And yes, you are effectively limiting it to only doing that thing a maximum of once per frame. But if the probability of it happening is sufficiently low, then it's not very common that you get it happening more than once per frame anyway. So it's a good approximation. And if we make these numbers even bigger, the approximation becomes even better. If you think about it, in this particular scenario, there's only a 0.02% chance of having a firework go off within any given 1 millisecond interval. So the chance of multiple fireworks going off within that interval is pretty tiny. But as mathematicians, we like to do things properly. And if it gets better by making n larger and making p smaller, what happens if we take it to its logical extreme? What if we could follow this on further and further? In fact, to see another important feature of what's happening, I'd like you to have a go at working out the variance for each of these distributions. You might remember the formula. These are in the formula book as well. E of x is given by n times p, the number of trials multiplied by the probability. For the variance, you just go one step further and multiply by 1 minus p, the probability of failure. So give that a try for these three. You can pause, work out your numbers, and then unpause. For our first one then, 60 times 0.2 gave me the 12. 60 times 0.2 times 0.8 will give me a variance of 9.6. For the next one, the 1 minus p term is actually 0.98, which is very close to 1, meaning the variance is now very close to the expectation. And it kind of makes sense that that's going to continue. We get a variance of 11.9976 when the value of p is so close to 0 that the value of 1 minus p has become really close to 1. You can see why this is going to continue. And the logical consequence of this will be something a little bit weird like this. A binomial distribution where effectively we've got an infinite number of trials because it's an infinite continuum of time, and the probability of success in any one of those infinite trials is effectively 0 because we're shrinking the probability smaller and smaller as we make the number of trials bigger and bigger. And we're trying to approach the point where the variance and the expected value are identical. And of course, we don't really want to be working with infinities and zeros in this way. But what we do instead is we define a whole new type of distribution called the Poisson distribution, which is built specifically for this kind of situation. It has a few interesting properties that are similar to the binomial and others that are very different. But one important idea here is that we can use the fact that the expected value and the variance are exactly the same value, and it's effectively the same as taking binomial to the infinite extreme. And now we don't need to worry about a fixed number of trials. We know that the number of trials is effectively irrelevant. It's not that we have a certain number of trials, it's that we have a certain period of time or a certain length, a certain interval, and we can work directly with that. Here's a few more examples of where a Poisson distribution is going to be the best way of describing what's going on. A call center getting an average of 40 calls per minute. So think about the fact that this average rate could be scaled up or scaled down. You could turn it into 2,400 calls an hour. But the important thing here is that there's no fixed number of moments when you could get a call. It's just that calls could happen at any point along a continuum of time. People walking into the ER, however many new patients you get. If you get a new patient on average every 2 minutes, you're talking about an average of 30 patients an hour. You can again scale that up, but you can ask questions like, if the average expected rate is 30 patients an hour, what's the chance of getting more than 40 during the next hour? Or what's the chance of the next person arriving within 1 minute? Questions like that can be answered using this distribution. We can look at how many cars go past a checkpoint per hour. You can even use this to explore things like, what's the chance of a 400-meter asteroid hitting the Earth? Because that seems to happen roughly once every 100,000 years. So you could ask the question, how many of those would you expect to hit Earth during the next million years? And what's the chance of us getting through the next 200,000 years and avoid them entirely? Neutrinos are notoriously difficult to detect because they basically don't interact with anything much at all and zip straight through the Earth. But there are special devices that have been devised specifically to slow them and stop them. And we detect about 4,000 a year. So those we seem to detect randomly and yet at a constant average rate. So we could use Poisson for that as well. Another example is this fiber optic cable. There might be flaws at an average of 2 flaws per 10-meter length, in which case, if you've got 100 meters or 1,000 meters, you could confidently predict how many flaws you might expect. But the Poisson distribution would let you put a number on the probability of getting 12-meter cable without any flaws, or probability of getting at least or at most a certain number of flaws. I'm not going to dwell on this very long, but I wanted to bring it up briefly just to show the similarity in terms of the distribution shape. With a binomial distribution that's got similar parameters, you'll find that there's not a huge difference between binomial and Poisson, but there are some important differences. For instance, in the Poisson distribution, there is no maximum value, although it'd be very unlikely if you're selling approximately 5 paintings an hour. It's very unlikely that you would sell 20 or 50 or 100 paintings in a given hour, but it's not impossible according to this. It's more like this distribution tails off just like the normal distribution does, and in fact the formula for calculating probabilities does involve the exponential function just like the normal distribution does. Let's have a quick look at a classic example. If 500 meteoroids hit the planet every year, which is in fact roughly the case, then we could ask the question, how many would you expect to hit the atmosphere in the next decade? 10 years. Well, that should be a nice, simple one to think about, because essentially we're scaling things up. 500 meteoroids per year is the average expected rate, and if you scale that up to 10 years, you're going to have 500 times 10. What about in the next week? So 500 a year, we're looking at something in the region of 10 per week. Now imagine then we decide that we're going to create a random variable that represents the number of meteoroids that hit the Earth today. Before you get too concerned, a chunk of space rock up to a meter across is actually nothing to be concerned by. If 500 of them are hitting the planet every year, if it was a big problem, then we'd already have a big problem. These chunks of rock are sufficiently small that they're going to burn up completely in the atmosphere most of the time before even a scrap of them ends up getting through to the surface. And hey, if they do get through to the surface, chances are they'll land in the wilderness, or more likely somewhere out at sea. But pretty much anything up to the size of a small car, we're going to be safe from, because it's going to burn up as it goes through the atmosphere. Anyhow, let's use X to represent the number of meteoroids that hit the Earth today. And we're actually going to calculate using the Poisson PD mode on the calculator that exactly 1 meteoroid hits the Earth during the next 24 hours. Poisson PD mode asks for just 2 things. One of them is X, that's the value you're calculating with, so how likely is it that we get exactly 1 hit? And the other variable is called lambda. Lambda represents the thing that is actually the same for Poisson distribution, the expected value, but also the variance. So the simplest way to think of it is the constant average rate, which in this case will be the average rate of meteoroid hits per day. If it's 500 per year, scale it down. 500 divided by 365 gives you the rate per day. And then when you ask it for the answer, it's going to give you 0.348. So that is the probability of getting exactly 1 meteoroid hit today.